Hi there, welcome to this lecture series on matrix algebra. This is lecture 24, part 1. The topic is on powers of a matrix. We will cover related topics such as the trace and further properties related to eigenvalues and eigenvectors. Let's get started. First, we look at computation for the powers of a matrix. Given a square matrix A, n by n, we seek a formula to compute the power a to the power k, which is a times a times a k times. First, we notice that in the case where A is a diagonal matrix, computing the powers is very easy. So let's say we have a diagonal matrix, we call it D, and on the diagonal we have lambda 1, lambda 2 to lambda n. And then D to the power k is also a diagonal matrix, where on the diagonal will be lambda 1 to the power k, lambda 2 to the power k, all the way to lambda n to the power k. And this fact can be easily verified. And next, we now assume the matrix A can be diagonalized, so that there is a matrix P invertible such that P inverse times A times P is the diagonal matrix. Let's call it D, and the diagonal elements are lambda 1, lambda 2 to lambda n. So here in particular, P could be the eigenvectors of A, linearly independent, and the lambdas would be the corresponding eigenvalues. And if that is the case, and then we can write A also as an expression for D and P. So starting from this expression, you can multiply on the left by P, then you have P inverse, which is identity, so you get PD. And then you multiply on the right by P inverse, and then P times P inverse is identity. So on the left you just get A, and then you multiply it P inverse on the right of the D. And therefore A would be P times D times P inverse. So using this, we can write out the powers of K. If we want to compute A to the power k, let's put in the expression for A and using the diagonalized form. So we have P times D times P inverse to the power of k. And then let's write this out k times, once, twice, and 3 times, and so on and so forth, all the way to k times. And then since the multiplication of all the matrices, you can remove the bracket. You can take any of the nearby products first. So what we could do would be, we notice that there's a P inverse and there is a P. So it's convenient to do this product first, because then you get the identity. Okay, and so is here and here. So between those brackets on the left and on the right, you get a pair of P inverse and P. So let's do that. Then we'll have PD from the leftmost one, and then we get this pair, and we get the diagonal matrix, and then we get again P inverse and P, and so on and so forth. All the way to the last one, we'll have D P inverse left. So all of these are identity matrix, so we can drop them. And what remains in the middle is D times D times D k times. So it's D to the power of k. So we have P times D to the power of k times P inverse. Now we have derived a formula to compute A to the power of k for every number k. So this will equal to P times D to the power k times P inverse. Now let's take an example. We want to compute the power of a matrix A, which is written here. So 7, 4, and 3, 6. So we see that we need to find the matrix D and the matrix P. that means we need to find the eigenvalues and the eigenvectors. So let's compute the eigenvalues and eigenvectors as the method that we have already learned. So I skip the details, and then we will find that lambda 1 is 3 and lambda 2 is 10, and v1 is this vector negative 1 1, and v2 is this vector 4 and 3. These are two eigenvectors. Now we can form the P matrix by collecting the two eigenvectors. I fill it in, and that's the P. And this is an invertible matrix, and then we can, using the method we have learned, we can find the P inverse, which is this. So this tells us that if we compute P inverse times A times P, we'll get a diagonal matrix, let's call it D, which will have the corresponding eigenvalues on the diagonal, so it's 3 and 10. So furthermore, this shows that A would be P times D times P inverse. Now we're ready to compute the A to the power of K, which will be P times D to the power K and P inverse. And let's put in all those matrices and write it out, and this is what we get. One important property of a matrix is called the trace. Let's look at the definition first. So you have an n by n matrix, a square matrix, A, and the trace of the matrix is defined as follows. So let's A be like this with elements A, I, J, and then the trace will be the sum of all the diagonal elements, which are in red here. So trace of A will be A11 plus A22 all the way to ANN. So we see that it's actually a number that is easily calculated once a matrix is given. Taking some trivial examples now, the trace of this matrix would be just the sum of the diagonal, 7 plus 2, which is 9. And the trace of this 3 by 3 matrix will be the sum of the diagonal, 5, 3, negative 2, which is 6. So as it turns out, the eigenvalues are related to the determinant and the trace of the matrix as stated in the following theorem. So the theorem says, let A be an n by n matrix, and the eigenvalues of A will be lambda 1, lambda 2 to lambda n. And then we have the following. The determinant of A is the product of all the eigenvalues. So determinant of A is lambda 1 times lambda 2 times all the way to lambda n. And the trace of A is the sum of all the eigenvalues. So lambda 1 plus lambda 2 plus lambda n will give you exactly the trace. We can take a simple example where A is a 3 by 3 matrix like this. So we can carry out our computation and find out the eigenvalues. You will find that lambda 1 is 8, lambda 2 is 2, and lambda 3 is 2. And then the determinant of A, once these are given, can be computed just as the product of these three, 8 times 2 times 2, which is 32. And you can also carry out the calculation of the determinant of A by any of the methods that we have learned, and you will find 32. So confirming the theorem. So part 1 of the theorem. And if you add up these three eigenvalues, 8 plus 2 plus 2, you get 12. And you will see that that's exactly the trace of A. That's 3 plus 6 plus 3. So 12. So we verified the theorem, at least for this one case. Let's now do a proof for the theorem. Part 1 says that determinant of A is the product of all the eigenvalues. Let's now first find the characteristic polynomial for the matrix A, we call it P of lambda, which will be the determinant of A minus lambda I. And if I know that the lambda i's are already the eigenvalues, and then we can write this out as a factorized form, where these lambda i's are already the eigenvalues of A. So in this formula, if I take lambda to be 0, what do we get? We get P of 0, the characteristic polynomial evaluated at 0, would equal to the determinant of A minus 0, so it's just determinant of A, and which will be, you see on the right hand side, lambda is 0, so you just get lambda 1 times lambda 2 times lambda n. And that's exactly what we wanted to prove. Part 2, the trace is the sum of the eigenvalues. Let's prove this for a 2 by 2 matrix. Let's say we have a 2 by 2 matrix. A has element A, B, and C, D. What is the characteristic polynomial? Well, it's the determinant of A minus lambda I, which is here. And if we work this out, so it's this times this minus this times this. And then you can open up and write it as a polynomial of lambda. So you will get lambda square, and you would get the first order term and the constant term. Let's call this equation 1. Now let lambda 1, lambda 2 be the eigenvalues. This means that the characteristic polynomial can be written out as this factorized form, lambda minus lambda 1 times lambda minus lambda 2. So I can distribute and open this up and write it again as a polynomial of degree 2 for lambda. So I'll have lambda square minus the first order term will be lambda times lambda 1 plus lambda 2, and then plus lambda 1 times lambda 2. Let's call this equation 2. Now we see that for equation 1 and equation 2, the left-hand side is the same. So the right-hand side must be the same. And that should be the same for all lambda, which means they have to be identical to each other. So if you compare term by term, they must match. So the first term is okay, and then the second term will give you A plus D is lambda 1 plus lambda 2, which we write here, and then A plus D is just trace of A. Okay, so this says that the sum of the eigenvalues is the trace of A. And then the constant term here, AD minus BC, should equal to lambda 1 times lambda 2, which we have here. And what is AD minus BC? Well, that is AD minus BC, so that's exactly the determinant of the matrix A. So here we actually also kind of approved it also for the property number 1. We now look at a special case of matrices, that is, we look at the upper triangular matrices. So, an upper triangular matrix, A, m by n, will look like this. So, under the diagonal line, which is red here, down here it's all 0. So in this case, there are some properties that helps us to find many of the things that we're interested in. So first, the determinant is the product of all the diagonal elements. And then, by definition, the trace is the sum of all the diagonal elements, which are in red here. And furthermore, the eigenvalues are precisely all the diagonal elements. So you see, for upper triangular matrices, the diagonal elements are so important. So in this case, the statements 1 and 2 in the theorems, they are obviously true because of this property here. Now let's do a quick proof to show that the eigenvalues of an upper triangular matrix will be the diagonal elements. So we can form the characteristic polynomial, which is the determinant of A minus lambda I. So writing out the elements in A, we'll have minus lambda on all the diagonals and 0 or under the diagonal. Then the determinant of a matrix like this, which is also upper triangular, would be just the product of all the diagonal elements. And this is so convenient that it's already written in the factorized form. So finding roots will be very simple. So each term will contribute to a root. And therefore, they are exactly all the eigenvalues. So lambda 1 is A11, lambda 2 is A22, and lambda n is ANN. So this is the end of part 1. And in the second part, we'll continue our discussion on related topics. So I hope you enjoyed this one, and I will see you in a bit.